Today, I want to give you like a rather intuitive introduction to all those topics. And if you read geometry of quantum states, you might think, oh, this sounds complicated. But I mean, we will take it step by step. So first, the question is like, what is geometry? So I mean, Google tells me that geometry is the branch of mathematics that is concerned with the properties and relations of points, lines, surfaces, solids, and higher dimensional analogues. And this kind of means that the geometry of quantum states means where are quantum states in relation to each other. And in our case, because we are interested in NISQ applications, we talk about parametrized quantum states. So, and this means we actually have like 3 different arenas we care about. So the first is the actual space where the parameters live. Yeah, this is like on this cube on the left, and it's like this fig theta. And then through some kind of parameterization, you will get like this parametrized quantum state associated to the parameters, rho of theta. And because we are classical people, we kind of have to always measure at the end. Yeah, so we have to perform some kind of measurement, which means we also have like the space of probability distributions over the measurement outcomes. Yeah, and what I try to visualize with these like red and blue lines is that a large change in parameter space need not necessarily carry over to a large change in the space of quantum states, and a large change in the space of quantum states must not necessarily be visible as like a large change in the output probability distribution. Yeah, so those are like 3 different arenas in a certain sense. And why are those important? So because we encountered them in variational quantum algorithms, where the parameterization is through like a quantum circuit. So you know, for example, you have the angles of your gates that are the parameters, or in quantum metrology, where it's like an implicit parameterization, where you say, okay, you have an unknown magnetic field, and depending on that value, you see other states if you evolve for a fixed time, for example. Or in quantum optimal control, where you say, okay, the parameters are how long and which kinds of control pulses you apply. And before we jump right in, I mean, this talk is based on the paper that you find in Quantum, and where all of those ideas are laid out in hopefully intuitive way. Okay, I put the QR code, but I also put it up again at the end. And now let's jump right in. So first, we said we are looking at the geometry of quantum states, which means we need to measure distances, because otherwise we don't really know where the quantum states are in relation to each other. And because we talk about parameterized quantum states, we also want to understand those distances in parameter space, because these are the things we can really adjust. These are the things we can vary. Yeah. And because I just like said that in parameter space, if you change a parameter, I mean, maybe your underlying state doesn't change at all, because, like, for example, it's invariant on this particular gate at this point in parameter space. Yeah. So what we do instead is we perform a so-called pullback of a distance between quantum states. So we take some distance d between quantum states and say, okay, the distance between the parameter values theta and theta prime is just the distance of the associated quantum states. And we can obviously also do this for the associated output probability distributions with some distance between probability distributions. And in the following, we will require that this distance is positive. Yeah, so there are no elements which have negative distance, and that 2 identical elements, they have distance 0. And we will also need differentiability of this distance. No? And this differentiability already alludes to what I want to do next. Yeah. So I ask myself, okay, what happens in the local neighborhood of one specific parameter setting? So you dial in a parameter setting, and then what happens if you just like slightly wiggle? Yeah. So why are we doing this? Often, like, knowledge about the local neighborhood is already sufficient to achieve what we want to do. For example, in gradient descent, you only go small steps anyways. Or, for example, in metrology, you usually know what your parameter is up to some margin of error that you want to make as small as possible. And I have like a small drawing for you. So this is like a very prototypical example. So we have 2 parameters, x and y. They parameterize some sort of quantum state, and we just like plot the distance from the state that has the particular values for x and y that correspond to this point. And you see that we get this kind of bowl shape. Yeah. And if you say, okay, but I mean, this bowl shape, it kind of already looks like a paraboloid. And so you can think about like really going to some sort of approximation to say, okay, what is like the paraboloid which really smoothly approximates this function in this neighborhood? And this is actually what we're going to do. Yeah. And what we're mathematically doing is we perform a Taylor expansion. And because, so what we're doing is here, we go to a fixed point in parameter space, theta, and say, okay, we wiggle theta slightly by this perturbation delta. And this Taylor expansion just tells you because, I mean, if we have delta 0, we know this must be 0 just from our assumptions. Yeah, identity of indiscernibles, so distance is 0. So this, and because it's like a minimum, we know that the first order will be a second order. And now this matrix M that appears here, yeah, it kind of tells us how this paraboloid is shaped, how it is rotated, how steep it is. And we can also give like a formula for this matrix because it's just like the Hessian, yeah, of the pullback distance relative to this fixed point in parameter space. And Hessian is nothing else but like a matrix that captures all the possible second derivatives at this point. Yeah. Okay. So we have taken this pullback distance, we have taken this Hessian, and then we now have the second order expansions. And so with that, we kind of already have some knowledge about what is going on in those small local neighborhoods. Yeah, okay. And why is this cool? So because this Hessian, it kind of gives you an inner product. So this Hessian is like always a positive matrix, just because like there's no direction in which your function can decrease. So it has always has to increase, so it's always a positive matrix, so it induces a scalar product. And scalar products are really useful because we can use it to measure lengths, we can use it to measure distances, and we can use it to measure angles. And we can now use it to measure those things, but taking into account information about the underlying quantum state or the underlying probability distribution. Yeah, and because of this, we call those information matrices. Now, the first information matrix I want to introduce you to is the classical Fisher information matrix. And it happens if we look at the output probability distributions. So we use the KL divergence as for the pullback, so the relative entropy between the output distributions, perform this whole process of doing the second order expansion, and what we get then is the classical Fisher information matrix. So I now call this matrix I because this is what you will find in the literature, but it's the same as M as before if for this distance we use the KL divergence. And we see here that we get some kind of object that quantifies how much the output probabilities, so PL is the probability of observing the Lth outcome, how much those probabilities change under the parameters theta I and theta j, and we weigh it inversely by like the probabilities of seeing those outcomes. And just to get like the intuition again, this classical Fisher information now quantifies how much a change of parameters of those thetas changes the underlying probability distribution that we measure at the end of our quantum experiment. Okay. And now you ask yourselves, okay, this sounds nice, this sounds straightforward. But how do we calculate it? How do I access it in an actual experiment? And to do so, we need two ingredients, just like from the formula. So first, we need the output probabilities themselves. And those are just like obtained from running the actual experiment, the actual circuit. Do it multiple times, compute a histogram, then you have estimates of those probabilities. Otherwise, you could also do more sophisticated stuff. For example, you could use a Bayesian approach, have some prior or distribution for those output probabilities, use some machine learning techniques. And the second ingredient is the derivatives of those output probabilities with respect to the parameters. And for those, you could either resort to finite differences, or you could use the parameter shift rule, which is just like a smarter way of getting those derivatives on quantum hardware or near-term hardware. And before I continue to the quantum case, I wanted to tell you a fun fact, and it's about the uniqueness. So, because like we can ask ourselves, okay, what happens if we use a different distance? If we do not use like the KL divergence, or which is the relative entropy? What if I use like, for example, fidelity distance or something like this? Yeah, and there's a theorem for that. And it's like a very celebrated result by Morozova and Chensov, which says that like the information matrix associated to any monotonic distance measure between probability distributions will be the positive scalar multiple of the classical Fisher information matrix. So Now, the first question is, what is monotonicity? Yeah, a monotonic distance measure fulfills these inequalities, which says that for any stochastic map, the distance can only decrease. What does this mean? So a stochastic map is just like a description of a process that kind of, for example, scrambles your probability distribution or some noise that you get on the measurement. And what it says is that if you have two probability distributions, P and Q, you cannot make them more distinguishable, so farther apart, by applying such a process. And this is actually an extremely reasonable requirement for any distance. And I mean, I think this result is kind of really mind-blowing in a certain sense, because kind of no matter what reasonable, in the monotonicity sense, distance you take for probability distributions, the local structure will always kind of look the same. Yeah, this is like, it's really like a crazy result. Okay. Now, let's go to the quantum. And obviously, as you might have already guessed, there is also a quantum Fisher information matrix. And I'll tell you like the derivations for pure states. And what we do is we really use the same process, but instead of like this KL divergence, we take some distance for quantum states. And in our case, we use the fidelity distance. Fidelity is a measure of similarity for quantum states. So if we do 1 minus fidelity, then we get like a distance measure. Okay. And if we do this whole process again, we get the quantum Fisher information matrix, which has entries which now look like this. Yeah. And you already see it's like getting a little bit more complicated. Yeah. So you have like those quantum states as objects appearing, which are in principle not accessible to you as an experimenter. You always have to do some measurements, which already hints at the fact that this will be like more or harder to calculate. And but you still see that like the intuition behind it is kind of similar. So you see really how, or you quantify how much the underlying states change with the parameters, and you quantify how much those changes interrelate with each other, which is like the first term. And but again, to give the intuition, this quantum Fisher information matrix quantifies how much the change of parameters, those feeders, results in the change of the underlying quantum state. And for pure states and for parameters that are encoded via parallel Hamiltonian evolution. So for example, think of a quantum circuit. On the first qubit, you do a Pauli Z rotation, and in parallel, you do a Pauli X rotation, for example. Yeah, this I mean with parallel Hamiltonian evolution. And for this, you have a rather simple formula where you say, okay, you can just like take what you would call a covariance of those two operators of Z on the first qubit and X on the second qubit, and it would give you like this Fisher information directly. No? So it's just like really, if the expectation values of those Z on the first qubit and X on the second qubit really vary together, yeah, then those parameters must be really correlated. Yeah, so it's also kind of telling you how entangled the state is that comes in at this point of the circuit with respect to those two gates. And other than that, in the pure state case, you can also help yourself with like some tricks. Yeah, so you can use perturbations of those fidelity distances in circuit that evaluate the fidelity. You can also use tricks with the parameter shift rule, which actually was an exercise last year for QHack. And you can also get approximation on the matrix level. If you say, okay, I don't want to compute the whole matrix, but only some entries, but like in a stochastic way, you can use an analog of SPSA for that. And as I already hinted at, like this is like for pure states. For noisy states, this gets even more complicated. Yeah, because in principle, you would need full tomography of this whole state, which is really, really hard to calculate this quantum Fisher information for noisy states. But I mean, people have been thinking a lot about that problem too. Variational methods, for example, have been proposed, but those are more suited for smaller systems because you have kind of high overheads, especially for NISQ, and you kind of rely on the success of some subroutines, which are also variational in nature. And but if you are happy, like not with an exact calculation of the Fisher information, but some sort of approximation, you can use, for example, the truncated quantum Fisher information. So only look at like the largest components of the quantum state if you want, and some hierarchies which can be computed from classical shadows, which is just like an efficient classical approximation scheme for quantum states. Now, I told you this fun fact with the uniqueness of the classical Fisher information, and there's also a fun fact about the quantum Fisher information, which is that it's totally non-unique. So there's this theorem by Petz, which says that there are infinitely many information matrices arising from monotonic distances between quantum states. And monotonicity is kind of defined in the same way, but now we don't have stochastic maps, but we have what we call quantum channels. So quantum channels, they just like describe anything that can happen to a quantum system, be it a unitary evolution, be it like a noise process, be it like a measurement even, yeah? And it just like says, okay, you cannot make two quantum states more distinguishable by applying some process of that type, for example, a noise process, which also makes a lot of sense. And the fish information I introduced to you, I mean, it's like one of infinitely many, but it's like the smallest quantum fish information that you can define in that way. And it's also known as this SLD quantum fish information, which is because you can also define it in terms of so-called symmetric logarithmic derivative operators. And if you're interested in the details of that, I suggest you have a look at the paper. Okay, now, there's one important relation between the classical and the quantum fish information I want to highlight. And namely, if we look at this monotonicity property, yeah, just like, okay, you cannot make stuff more distinguishable by applying some quantum channel stochastic map, which you can write like this, it kind of implies that the information associated with those distances can also only decrease. And you might be a little bit confused because those are matrix inequalities. I have like this small picture which tells you that like you can like morally say that like the one matrix has larger eigenvalues than the other. I mean, it's also about like the alignment of those eigenvalues, but this is one way of thinking about it in an intuitive way. And now we can use the fact that measurements are also quantum channels, and that the quantum fish information for a classical state, so just like a diagonal density matrix, is actually equal to the classical fish information, which means that if I perform a measurement, the fish information I get is always upper bounded by the quantum fish information of the original state. So we have derived that the quantum fish information is really an ultimate bound for any classical fish information that can arise from any measurement you could perform. So you will never be able to really exceed this quantum limit if you want. And this directly brings us to the roles of the classical and quantum fish information. So first, we have the quantum fish information, which is really quantifying the ultimate limits. So it's really like there's more to be done than what this quantity is really giving you. And it also tells you a lot about like the quantum effects that are happening in your system, for example. And on the other hand, we have the classical fish information, which quantifies the behavior for one fixed measurement. Yeah, you can obviously optimize over measurements too, but you will never beat the quantum fish information. But this classical fish information is extremely relevant in practice because, I mean, in the end, you have to measure something. Yeah, you can't get around measuring anything. Yeah. Okay. So I hope that wasn't too fast until now, because now we're already like looking at some applications. So the first application I wanted to highlight is quantum metrology. And this is really like where those tools kind of come from in a certain sense and where they have been used the most. So quantum metrology. So first, physicists are usually very interested in measuring quantities, yeah, magnetic fields, energies, temperatures. And metrology is like just like the scientific study of measurement processes. And in quantum metrology, we then study how quantum effects can help. And a typical metrological protocol can be described in the following way. So first, you start with a probe state. So you prepare a quantum system in a particular state, and then it will undergo some kind of what we call the encoding evolution. So for example, you prepare some spins, let them point in some directions, and then let them undergo a precession under magnetic field for 10 nanoseconds, fixed time. And afterwards, you perform a measurement. Yeah? And from this, you can get some kind of output distribution. And this is just like really like a general way of viewing how a metrology process works. And to see this a little bit in more detail and get us some intuition, I have prepared some slides, or one slide. And so we look at the following problem. We want to estimate a phase, which we can see is like evolution under the Z operator for some unknown phase phi. And to measure this, we prepare a plus state, and at the end measure in the plus-minus basis. Yeah? So side note, I mean, if we use, for example, the 0 or the 1 state, then nothing happens. So we can't measure anything because like those states, they don't evolve under like, they don't pick up a phase. No? Okay, and now you have this experimental setup, you fix this metrological protocol, and then you can do the theory. So you say, okay, if you do the theory, if I have a parameter phi equals to 0.9, I get this histogram over outcomes. And for 0.5, I get this histogram over outcomes. And then you say, okay, I now did the theory. And then you go perform the experiment. And then you see this histogram. And you're not completely sure about this histogram. So you put some error bars. And now what you do is like, okay, you go back to your theory and say, okay, it looks like phi is 1.1. And yeah, I'm not so completely sure. So plus minus 0.1, depending on the error bars. And what this is essentially what people call maximum likelihood estimation. So you just like output as an estimate for phi, that phi which is most likely to have produced this particular histogram that you observed in your actual experiment. Okay, so this is how you would approach such a metrology problem in practice. And now, what is cool and where this Fisher information stuff is coming in is via the Cramer-Rao bound. So what we formally did in this process is, or mathematically formally, is we constructed an estimator for this physical quantity, namely this phase, from the output probability distribution. And I use this curly phi for this estimator. And we call it unbiased if in expectation, we will actually output the correct parameter. So if we try enough and average, I mean, we should get like the correct outcome, at least in expectation on average. And now, for any such unbiased estimator, the Cramer-Rao bound limits the best precision you can actually achieve, and it looks like this. So what is happening here? So first, on the left-hand side, you see that you have the covariance matrix of this estimator. And you can see that it's like, for example, on the diagonal entries are just like the variances of the different components. So, I mean, if the variance of your estimate is very large, it varies a lot. So you're not very sure about your estimate. So you want a small variance. And we can also maybe understand this more intuitively, seeing that the trace, so just like the sum over diagonal of this matrix, is nothing else as the mean squared error of this estimator, which is maybe a more familiar quantity. Okay. So on the left-hand side, we have this covariance matrix that captures how well you're estimating. And on the right-hand side, we see we have a lower bound. So there's like a lower bound to the variance, which means there's an upper bound to the precision you can achieve. And it actually involves the classical Fisher information relative to those parameters that you're trying to measure and the inverse of it. So what does this mean? It means that I can estimate well, so with high precision and low variance, if I have very large Fisher information. The intuition is that if I have large Fisher information, then changing the underlying parameter, the ground truth, will result in a very different probability distribution that I observe. So it's harder to discern, or it's easier to discern this probability distribution, so I can be more sure about my estimate. So this is also why the inverse is coming in here. And this 1 over n in front is just like if I perform n repetitions of the experiment. Okay, and because we saw that like the quantum Fisher information is upper bounding all the possible classical Fisher informations, we immediately get this quantum Cramer-Rao bound on the right-hand most side, where you say, okay, really like there's an absolute limit. Also, if you optimize over all your measurements, if you do very well, you will not be able to beat this like quantum limit. So that was like the 4-minute foray into metrology. And now I also want to give you like a sneak peek into an application which is more related to variation algorithms, namely quantum natural gradient. And like from looking at like the talk rooster, I think we will also hear something in that direction again this week. Okay, so, but what is quantum natural gradient? So first, I think most of you, because like this is also about quantum machine learning, have heard about gradient descent. Yeah, it's just like a general purpose method to minimize a cost function of many parameters. So you take the gradient and then you walk in the other direction. Say, okay, I walk where the cost function is actually decreasing the most. And we can actually reformulate this update rule as an optimization problem. Okay, this might not look like we simplified things, but we can get some more understanding of what is actually going on. So first, on the left side, we have this term which is just like minimal if our update points in the opposite direction of the gradient. So we really want to go where the cost function decreases the most. Yeah? But on the right-hand side, we also have this regularization term, which avoids overstepping, because like the gradient is also only like a local approximation. So, I mean, it will not be valid if we step too far. Yeah, and this is also where this either the learning rate is coming in again. Yeah, okay. So this is like this regularization term with the 2 norm. And now, at the start of this talk, I hope you remember, we started realizing that, I mean, changes or measuring distances in parameter space, just like in the Euclidean distance, is maybe not such a good idea. Yeah, and instead, if we now instead use like the pullback of like this quantum distance, and we replace this regularization term with the one induced by the quantum fish information matrix, yeah, then we get a new update rule, which is a quantum natural gradient update step, yeah, which is just like involving the inverse of the quantum fish information matrix. So intuitively, this kind of means that because we take the inverse, so if we have like a gradient update in a direction where the state changes a lot, so high fish information, we regularize it and make it smaller. And if the state doesn't, the underlying state doesn't change a lot, we actually make it larger. Yeah, which means that we really adjust the updates such that in the space of quantum states, we are doing relatively smooth updates in all directions, if you want. Yeah. So the cool thing about this is that this update rule now really takes this underlying geometry of the quantum states into account. Yeah, so I mean, this is cool and intuitive, but you might ask yourselves if this actually helps, because like, I mean, it's not a priori clear that like taking this particular structure into account is helpful. But there was this paper from which I took a figure by Viris, Gogolin, and Castellano. And they really compared quantum natural gradient with state-of-the-art optimizers, so Adam and BFGS, for a wide range of qubit numbers. Yeah, and I mean, it's going until, I think, 40 qubits. And I mean, they only were able to do this because they were looking at a free fermionic model, where you can actually push your simulations to 40 qubits, I mean, without a supercomputer. And but what they saw and observed is that this quantum natural gradient really outperformed consistently the other optimization methods. And also because it took different optimization paths. So it was not running into certain local minima that you would otherwise have walked in. Yeah. So this was like the short foray into applying those quantities, classical and quantum fish information, for VQAs, for variation quantum algorithms. And with that, I'm actually already at the end of this talk. So, and I want to conclude with an outlook. So first, this fish information, both classical and quantum, is like a very versatile tool. And it has also found applications outside of NISQ. Yeah, so also in theoretical quantum information, error correction, resource theories. And because those parametrized quantum states, they are really fundamental to those NISQ applications. So they really pop up everywhere. You know, variation algorithms, metrology, optimal control. I really expect that there are many more interesting applications of fish information arising. Yeah. And because of that, also really a lot of open questions remain and a lot of work is still left to be done. So it's really also fun to work with those quantities, try to find applications and really explore what they are capable of. And with that, I already want to thank you for your attention. I again put here a QR code for the paper, and the right link is to my webpage, where I will upload the slides shortly after this talk.
Great. Thank you very much, Johannes. I love the QR codes in the slide deck. That's awesome. Johannes, I noticed you're wearing some QHack swag. Could you show it off to everyone in the audience? QHack 2022. How do you like it?
Oh, it's awesome. But it's not as awesome as your tie-dye. So I'm really like a little bit envious, actually.
The tie-dyes are available as special swag kits for some lucky winners throughout QHack.
Okay, maybe I should also take part this year, if that's the case.
Watch out, everyone. All right, Johannes, I'd love to do a little bit of a personal interview for you now, and get to know the scientist behind the science. So I've got a few questions prepared. Why don't we start with your time actually in university, where it's always amazing to me when I hear someone from Europe say they struggled to learn a language, but they tell me in English that this is the case. And then they kind of master the language, because I mean, do you just take English for granted as a language that, it naturally comes to you?
Yeah. Yeah, I mean, like English is like, I mean, second language, right? It's like, also in Germany, you are forced to learn it like from kindergarten, not in kindergarten, but, from elementary school, you're like drilled. Like, I mean, we have like a lot of English experience. And I mean, if you work in science, it's really like, yeah, I mean, you can't get around it. It's also good that there's like one common ground that everybody agrees on, that we talk English. Yeah.
So kind of a natural advantage of being forced to learn it from a very young age. It's ingrained.
Yeah, I mean, it's also natural advantage if it's your mother tongue, but I mean, I think it's like not problematic. I mean, it could be way worse. Imagine if everybody had to speak German. Yeah.
J-Man, German's a beautiful language. I love it. I wouldn't mind.
Yeah, beautiful maybe, but not necessarily easy.
Not easy, no. It's like a hard version of English. Johannes, I heard you're actually trilingual. Is that correct? Is that a good assessment?
Yeah, I mean, I speak French because like I lived in Montreal for a year. So, but I mean, some people might argue that I'm not speaking French, but Québécois.
So you speak the true Quebecois French.
Wait, I was like, it's like I'm from a very rural part of Bavaria, and so I grew up with like a rather strong dialect, and like also when I moved to Berlin, I really had like difficulties communicating sometimes, and but I mean it kind of imprinted me with a certain love for dialects, and I really like Quebecois. It's just like it's a very nice way of speaking French, and it's like kind of a little bit more down to earthish.
I've heard that potentially Quebecois is more like true to the roots of the language because they were separated from France hundreds of years ago and it kind of developed on its own.
Yeah.
So
I mean, tell that to the French.
Yeah, I think there's no agreeing there. So Johannes, tell us about your time in Montreal. You spent a year there?
Yes, I spent a year there in doing my bachelor's actually, and this is also because like why I went into quantum information theory. Because like at the time I was like going there, and I mean it was at the end of my bachelor, so I didn't have any mandatory coursework I had to do. So I just like wrote to people there in this like Facebook groups and asked, I mean, what are the good courses? What are the ones I should take? And besides some really other amazing courses, I had like quantum information with Gilles Brassard at Université de Montréal, and wow. I mean it's like he's been doing this lecture for I don't know 16 years. And I mean, it's like, it was really refined and very intuitive. And it was just like extremely good. And I mean, he really conveyed like how fun it is to work on those problems. And then this is why when I came back to Europe, I just like asked Jens Eisert, who is also the quantum information guy in Berlin, essentially, to do my bachelor thesis there. And yeah, and so is how I slid into quantum information theory, essentially. And it's just because I went to Montreal.
Awesome. And I heard that after your time in Montreal, it took you a little bit of time before you made your way home. Could you elaborate a little bit what happened?
Yeah, I mean, I was essentially living like the dream of every exchange student, and like I saved some money. I actually worked as a TA during my time in Montreal and really collected money on the side and bought like one of those family vans, like Dodge Grand Caravan. And then, I had the mattress in the back, and then I just like went for the all-American road trip. So I spent like 4 months on the road, and all of the US and Canada, and this was like an experience.
By yourself?
It was really great fun. I mean, I had some friends over actually. So I mean, it was like 4 months, but then for 12 weeks of those 4 months, I had friends with me who were joining for different parts of the trip.
Any highlights from that trip? Any fun stories you can share?
I mean, I think like it kind of highlights like some of the carelessness that you have at a younger age in a certain sense, because like I vividly remember that I went to New York, and then like I just like opened Google Maps, was like, where do I sleep? I just like pointed to a random spot in Brooklyn, and like I'm going there. And then I just, just like parked my car there in the streets, and then slept.
What could go wrong?
Yeah, what could go wrong? And I mean, it's like I realized afterwards that like not all of Brooklyn is very gentrified in that sense. But yeah, I ended up in a neighborhood where people were essentially not caring at all, and it was actually quite fun. And so I can really recommend, like, New York City is like a nice destination.
Nice. And did you drive from Montreal down to the US?
Yeah. I really went like all the way. It's like only driving.
I heard there was some interesting stories at the border crossing.
Was it? I mean, like, surely. I mean, it's like, I mean, other than the fact that I sweated a lot at the border crossings, but it's like, I mean, if your visa is running out, and I mean, you know, like in the US, border controls are kind of tough. I mean, it's not like illegal immigration from Germany is probably that big of a problem, but I mean, you're supposed to go home after like 3 months of visa-free tourism and not come back. Yeah. And I mean, I tried to come back, and then it was like this decision. So either they let me in as like an exception, or I will never be able to enter the US again without a visa. Oh. So it's like, if you have been refused once, it's not so cool. But I was lucky. I was able to convince them of my good intentions, because like I just had to ship my girlfriend to the airport, and that was it. But yeah, it was like an intense hour, like waiting at the border post, that they were like allowing me to do this.
Thanks. All right. Did you have any? So this is fun because we have a musical theme with QHack this year. Did you have any like go-to soundtrack during your road trip?
Yeah, I mean, like, actually, I this was something I really prepared a lot, because, like, I mean,
that was the only thing you prepared.
Anticipating driving a lot.
You didn't prepare where you're going to sleep, though, right? You just prepared the music.
What did you say?
You didn't prepare the location for where you'd sleep every night. You just prepared the tunes.
Yeah, I mean both, but I mean not everything at once. But I mean the tunes I prepared very well, and it's like I really took like a week and really have like this like CD. I mean, I still have it somewhere with my road trip music, and it's like I mean the cool thing is, like, if you listen to one CD like really for like weeks, I mean you immediately know, like, when one song ends, your brain automatically starts playing the next one. And even today, if I hear like one of those songs and it fades out, I'm like, I know what comes next.
So what was your favorite one from that entire CD? Stood out the most?
Oh, I mean, I think like I think like Superstition was like top on the list.
Yeah.
Or like Man Eater. I think Man Eater is also a very good like road trip song.
Nice.
And the whole Need for Speed Underground 2 soundtrack.
The entire soundtrack.
Actually, yes. Yeah. I mean, actually, the entire song. I think I even had like 90% of the soundtrack on the CD.
Nice. So what are you listening to these days? Any bands you're particularly fond of at the moment?
Yeah, I mean, it's like, I mean, I'm mostly listening to harder types of music, but I mean, actually, my last year's like Spotify top favorite was Goa. It's like, this was like the Ukrainian contribution to the Eurovision Song Contest, and it's like, you know, like Ukrainian folk techno. So I can really recommend it. Like, try it out. This is like awesome music. You will maybe be confused like the first 3 times you listen to it, but afterwards it's really addictive.
Nice. I'll have to check that out.
Yeah, I'm looking forward to what you say.
So how about now we open up 2 questions for the chat. So please, people in the chat, send us your questions for Johannes. I will relay them on to him. Maybe I'll start with one of my own. So Johannes, I'm really big into geometry of quantum states as well. But I always find it interesting that there's always new things to discover that you would have thought, like geometry, quantum information, we would have figured that stuff out a long time ago. There's books on the subject, but there's always something new. So, you know, what interests you most about this particular topic?
So, I mean, first, I mean, it's obviously just like fascinating math. I mean, I guess like most people who encountered like these concepts, classical Fisher information, quantum Fisher information, also differential geometry of quantum states, it's just like fascinating. It's just like, it's nice to work with interesting concepts. It's actually a lot of fun. But besides that, I think like a lot of evolution in these areas of science, and I think this is also one of the reasons why we haven't really figured it out yet, is that you just like keep asking new questions. And especially like when we look at like NISQ applications, you know, like with parametrized quantum states, and especially, for example, parametrized quantum circuits, like one of those dominant models. And I mean, people were not technically really looking at that class of particular
That's true.
parametrized quantum states. And just because we have those new approaches and we have those new questions that arise relative to those new approaches, then we can say, okay, what can this tool tell me about it?
Awesome. Do you think that there's any area that's kind of underexploited or underrepresented?
Not particularly, I would think. I mean, like, one of the problems that you admittedly have a lot with those concepts, and, you know, like, also because they are so fancy and nice, is like you have like one of those typical hammer and nail problems. So you have like a beautiful, very intricately carved hammer, and you just like try to look for the perfect nail. And it's not always clear how to best make like this match between like the tool, Fisher information, and the actual problem. So, I mean, I think like, for example, this quantum natural gradient is just like a very beautiful, very intuitive way of doing it. And where you say, okay, this is like a clear cut, like it's the perfect nail for that hammer. And also for other things, I mean, there's also, for example, machine learning related things that you can do with this Fisher information. This works pretty well. But I mean, like, in many cases, I think we still have to find this match between hammer and nail to really bring out the best results. But I cannot really tell you like one area which is particularly underdeveloped. I mean, people really work along all the lines. And I mean, if there's something appearing where Fisher information is probably giving you some kind of positive contribution, or is like the right tool for the job, then people are trying to throw it on there and see if it sticks, you know. But yeah, so nothing which I would say is particularly underdeveloped. But I think there's like this underlying question of like, okay, finding really the right problems where this is really applicable. And people are finding like some here and there. But I mean, it's just like, it's just like a continuing developmental process.
Awesome. All right, I'm going to pull some questions out of the chat here. So we have a question from Veyrout. Is there a reason for using fidelity distance in the context of variational quantum circuits for machine learning on classical data?
I mean, there are reasons to do it and there are reasons to not do it. So, for example, fidelity is just like a very nice and very operational quantity in a certain sense. So you can also define it as like the optimal probability of discerning two quantum states. Yeah, it's related to that, for example, via the optimal measurement. And fidelity is also cool because it's very related to the natural inner product that you have in the space of quantum states. Yeah? So it's just like, it's a very natural quantity in that sense. However, fidelity also has some problems, which you could call, which people in other areas call, what was it again? No, I have forgotten the name, but it's some kind of catastrophe. I forgot which one it is. So the issue is that it is very easy to make states distinguishable in terms of fidelity. So because like Hilbert space is so large, just like making one state orthogonal to each other is really easy.
There's lots of room.
So there's a lot of room. And this kind of also reduces the applicability of Fisher information per se in certain areas, because you're just like losing information too quickly, because like there are too many states which are different from the state you're looking at. So it's really often a question to balance and to really find the right distance. And the cool thing is that we have like this infinite family of distances to choose from.
So question from Reckoning SA. Let me try and paraphrase here. What do you mean by more distinguishable when you're talking about geometry of quantum states?
So, I mean, usually you want to give those distance measures. So, I mean, the thing is like if you have like a large distance, it kind of means that those states are dissimilar in a certain sense. And so this kind of translates to like an intuitive notion of if they are very dissimilar, you should be easier job for you to distinguish between those two states if just like somebody handed you a copy of both of them and didn't tell you which one. Yeah. And usually for all those quantities, for those distances, be it like fidelity or, you know, like quantum relative entropy or any whatever entropy distances, whatnot, the thing is like usually also are given some operational interpretation. So if you perform this kind of task, and often it's like the kind of hypothesis testing that I just like outlined, where I say, okay, I have two unknown states, I give you one of them, and then you tell me like which one it is. Yeah, and often there are prescriptions of that type with certain limitations on your resources, for example, give you like an operational interpretation, for this quantity, because like there's like a maximum rate that you can achieve, and there's like an equal sign which just like involves somehow these quantities.
Cool. Why don't we take a question from Kiro QML? Can we use quantum information matrix to analyze quantum kernels? And is it possible to use the Fisher information as a direct distance measurement between quantum states?
So yes, and it's pretty natural, because like in quantum kernels, or at least like in those formulations you usually encounter, like in the vanilla quantum kernels, I mean, you're really looking at the fidelity between quantum states. So it's like just like if you have like two very close data points, then I mean this Fisher information matrix kind of tells you a lot about your kernel. Now, can we use it directly as a distance measure? No, because like, I mean, the Fisher information is kind of a local property. Yeah, so I mean, you fix like one parameter, and then to each parameter you associate one Fisher information matrix, which means like every data point has its own Fisher information matrix. Obviously, you can maybe cook up some things where you just like compare the Fisher information matrices associated to the different data points, but I would not see like an immediate like operational interpretation of that, or why this should be like a good idea.
Awesome. Maybe a bit more lighter question here for you. This is from your good friend M. Gil Fuster, and he asks, if you had to give up board games or bouldering, which one would you give up, and why bouldering?
Yeah, it's a good question. I mean, like board games or bouldering, I would say like bouldering is nice, and I really do it for fun. But I mean, I'd rather not give up any of those two things. But I think Elias also has some, what do you call it, skin in the game, because he's like really like the board game master of our working group in Berlin. So yeah, I'd rather not give up any of those two. But yeah, I mean, obviously, like playing with Elias is like one of the most fun things.
Nice. It's really interesting. I get to hear a lot about the speaker's background, and a few things are quite uniform across a lot of our speakers. Bouldering and board games seem to come up quite a lot.
Yeah, actually, I mean, like bouldering is like, it's like a disease. Everybody has it. Yeah. So I think also in our working group, like bouldering is like 50% of the people are actually doing it. And my guess and why this is so widespread in the community is just like because it's like an individual sport. So you don't need to have teams to perform it. You just like can go whenever you want. And it's also about problem solving. And this is really like the fun thing about bouldering. I mean, it's kind of sports, but I mean, in the end, you want to like solve a problem. And because I guess like most people in the field are just like having a lot of fun when they solve problems. So I think like they really enjoy bouldering. Also, it's quite hip at the moment.
Nice. All right. We got a question from DB Daniel _. It's a little bit of a different question. It says, hey, Johannes, where can we connect with you, especially aspiring quantum information scientists like me? I checked you up on LinkedIn and it was like ancient.
Yeah, okay. I mean, like, I really don't like LinkedIn. So, and I mean, I have a profile there. Maybe I should also delete it. I don't know. But I would say Twitter is the answer. So, I mean, like, I mean, my DMs are open. So, I mean, hit me up on Twitter. I guess that would be like the best. Also, I can just like recommend Twitter because, like, I mean, this whole quantum information bubble on Twitter is actually pretty cool. A lot of nice people. And what I really dig about it, and what I also try to do if I like come up with a paper or I understood a new tool or something, is just to write like a Twitter thread about it, which is like a very compressed way of sharing your knowledge. And I mean, if I see an interesting new paper, I just like check it out. I see new paper, then I go to Twitter and look up the authors, and then usually there's already like a very nice detailed explanation where somebody just like really digested everything for me. So it's like I can really recommend getting Twitter. Awesome. Do you have to censor this? The T word?
You heard it here, folks. Twitter is the new archive. So that is at JJ_XYZ if you want to connect with Johannes on Twitter. Johannes, that's all the time we have for now. It's been really great having you on, and thanks a lot for joining us.
It was my pleasure.